Problem 7 tells us that the half-pipe at a skate park consists of a tube of compacted snow with a semicircular cross-section of r equals 5 meters. We choose a coordinate system with the origin at the center of the cross-section and angle theta measured away from the vertical. A skateboarder of mass 50 kilograms on a frictionless skateboard starts at angle theta naught and begins riding back and forth in the half-pipe. Part A asks us to find the potential energy of the skateboarder as a function of their position theta. Here's what the situation looks like. The skateboarder is at the point where the solid line meets the semicircle. First, we know from introductory physics that the potential energy as a function of height h is u of h equals mgh, so we'll need to find an expression for h in terms of theta. This diagonal line has length r, and the height above the ground, h, is this little piece. So this big piece up here is r minus h, since the radius is constant along the semicircle. If we draw a line along the bottom, we see that we have a right triangle where r minus h over the hypotenuse r is the cosine of theta. Solving this equation for h, we see that h equals r times 1 minus cosine theta. We can now substitute this h into our original potential energy expression to get potential energy as a function of theta, which is u of theta equals mgr times 1 minus cosine theta. Using a gravitational acceleration of g equals 9.8 meters per second squared, a mass of m equals 50 kilograms, and a radius of r equals 5 meters as given in the problem statement, we find that the potential energy as a function of position is u of theta equals 2,450 times 1 minus cosine theta. In part B, the skateboarder begins to oscillate back and forth about the bottom of the halfpipe, and we're asked to find the angular frequency of these oscillations. We'll begin by writing down Newton's second law in polar form, which gives us a radial force and a force in the direction of theta, where Fr is m times r double dot minus r theta dot squared, and F theta is m times r theta double dot plus 2r dot theta dot. Luckily, r equals big R is a constant, so the first and second derivatives of r dot, and r double dot are both 0, which simplifies our equations quite a bit to Fr equals negative mr theta dot squared, and F theta equals mr theta double dot. Now let's take a look at the forces acting on the skateboarder. We have a normal force N acting in the radial direction and the gravitational force acting in both the radial and angular directions. In our case, we're interested in finding the frequency of the skateboarder's oscillations about the center of the halfpipe, but these oscillations happen only in the angular direction, not the radial one, so the radial force Fr, which keeps the skateboarder constrained to the halfpipe, need not concern us, and we can worry only about F theta. This also means we can ignore the normal force since it acts purely in the radial direction. Next, we'll need to find the component of the gravitational force that acts in the angular direction. To do this, we'll break down the force into its two components. I'll also rewrite W as mg, which will come in useful in just a second. Since the radial and angular forces are perpendicular, we now have a right triangle with mg as its hypotenuse. If we draw a vertical line through mg, we can clearly see that the angle close to the halfpipe is exactly the same as theta. This means that the sine of theta is equal to the angular component of the force divided by mg. By multiplying both sides by mg, we find that W sub theta is mg sine theta. Since W theta is the only force acting in the angular direction, we can set it equal to the expression we found for the angular force earlier. Notice that we now have a minus sign in front of mg sine theta. That's because the gravitational force is a restoring force. That is, it always acts to bring the skateboarder back to the center in the opposite direction as the angular displacement. Since we have m on both sides, we can divide it out. Then, we can use the small angle approximation, which says that at small values of theta, sine of theta is approximately equal to theta. Then, we divide both sides by r to get theta double dot equals minus g over r times theta. We'll now define a new constant, omega, such that omega squared is g over r, and place it into our equation. This second-order linear differential equation, whose solution gives us the skateboarder's position as a function of time, is the exact same as that of a harmonic oscillator, like a spring or a pendulum. We know that the solutions to this equation are of the form theta equals a cosine of omega t minus delta. Here, a is the amplitude of the skateboarder's oscillations, and it tells us how far the skateboarder goes in either direction. Delta is a phase shift that tells us where on the halfpipe the skateboarder started, and the final parameter, omega, is the angular frequency of the oscillations. We defined omega squared to be g over r earlier, so the angular frequency is just the square root of g divided by r, which in our case is just 1.4. If we want the non-angular frequency, we simply divide by 2 pi, which gives us f equals 1 over 2 pi times the square root of g over r, or 0.7 divided by pi.